But let's move on to our next speaker, Dr. Ali Bilgin. Dr. Bilgin is an associate professor of biomedical engineering, electrical and computer engineering, medical imaging, and the Bio5 Institute at the University of Arizona. You are in every department, feels like. He's also the associate department head for biomedical engineering graduate affairs. His research interests include signal and image processing and magnetic resonance imaging, among other things. And he will be talking to us today about denoising diffusion models in medical imaging. And I'm very excited to hear this. So, Dr. Bilgin, it is all up to you.
Thank you, Julia, for asking me to speak. And Ivo, I mean, that really is, I can't even ask questions because it really looks amazing. I would love to have a little bit more time to look into it, and it looks like a wonderful resource with all the different pieces put together. Okay, so let me share my screen, and I'll start with some disclaimers. I've given these to Julia already. She knows about that. So the work that I'm going to present work here that's not really my work. I mean, I'll show you a little pieces of things that I've done, but this will hopefully be mostly like a review for people. And then at the end, I'll show you some, fairly trivial things that I've done, just because this is so interesting. And that's one caveat. And then the other thing is that this area is so active that if I quit doing everything else and I just devoted my entire day to looking at these diffusion models, I don't know if I can catch up. There are so many new things coming up. It's really interesting, very exciting. Everybody is excited about these. So it's kind of trying to drink out of a fire hydrant, essentially fire hose. So it's just so exciting. But all of that said, and I'll try to go quickly over this presentation. I have a lot of slides, but I'll try to pick the ones that are of most interest to everybody. So I don't unfortunately know everybody's background. So here's a very quick outline, but some of these are very short, so I'll speak about them for only a few 30 seconds or so. Okay, so I'll introduce this deep generative models, talk about the diffusion models, and then I'll talk about a few recent extensions of these. And this little bullet at the end is what I've done with this. I mean, I've been playing around with it in some MRI applications. I'll just show you the things that I've done and what I imagine it could be used for also. I don't know if everybody is familiar with these two methods, DALI and DALI2. These are really very exciting text-to-image models that were introduced by OpenAI. I know a lot of people are now very excited and excited in quotes about ChatGPT kind of thing. So this is a very similar thing in the image side of things, right? So how these things work is you prompt the text, and the network, the model produces an image in response to your text that fits the description that you are providing. So here are some quick examples. So teddy bears working on new AI research underwater with 1990s technology. The machine the model produces this. It's pretty amazing. You see all the components in the text in that image. There are teddy bears, they're underwater, they are using what appears to be old kind of technology and so on. So here's one I generated, a wiener dog enjoying sunset at University of Arizona Mall. So here are a few images that I got out of this. It looks wonderful. I don't know if you've been to University of Arizona campus. We have a lot of red brick buildings that look like this. We have palm trees. We have really nice sunsets. And we had a wiener dog. So all of those on campus, this model is just able to create that just from that very simple text prompt. So it's really pretty fascinating. So these, just generally speaking, these deep generative models are neural networks that learn to approximate very high dimensional distributions, and then they're able to generate new samples from these high dimensional distributions, and they can also be used to calculate likelihoods as well. So this is a part where I'm not really sure how familiar people are with other generative models, but maybe I'll skip over this and assume that you may know a little bit. It's not super critical. I just want to say here that there have been earlier attempts for generating deep generative models, such as GANs, the adversarial networks, and then variational autoencoders. These all are generative models in the sense that you can once you learn a distribution, you can generate samples from that learned distribution. So in spirit, they are similar to what I'm going to talk about. So the diffusion models themselves are the latest generation of these generative models. And just very kind of intuitive description of what happens here is we start with a data point. I am personally interested in images, so I'll be talking about images. And then you carefully destroy the structure in this image, and then you characterize this destruction, and then learn how to reverse the destruction. So that's a very high-level description. So let's take a look at a little bit more the details. So let's say that we start with an image, and this image is going to represent our state 0. Now, if we were to take this image and add some noise to this image, we can generate a noisy version. And then we can add some more noise, generate an even noisier version. And if we keep doing this for a number of steps, specifically T steps, at the end, we are going to end up with this image that's essentially all noise. It's dominated by noise. So now, what these diffusion models do is they model this forward process as a very simple Markov chain with Gaussian transitions, and you can come up with distributions that define these transitions as very simple normal distributions with means and the variances, covariances shown here. Okay. And it's also possible to, using these Markov properties, it's also possible to model this steps, not necessarily one at a time, but you can model from step 0 to given step 0, you can also model step T in this way as well, right? So all of these are in the references. You can look at them in more detail coming up. Now, of course, we are not really interested in taking images and generating noise out of them. That doesn't seem super useful. We are really interested in the reverse process here for generative models. So we want to start from essentially noise and then be able to generate an image by following the reverse process. So in these diffusion models, some of them at least, I'll discuss this coming up. This reverse process is also approximated as a Markov chain, and the transitions are learned Gaussian transitions. What I mean by that is that you start with noise for the last stage, 0 mean, unit variance. And then you pass this through a network, which is defined by this parameter theta. And this network aims to estimate the mean at the next stage. Okay, so this is the network, and then this is what you use for learning process. Let me give you a little bit more detail of how practically that is performed. So you during training you randomly pick a step between 1 and T, and you generate Gaussian noise, 0 mean, unit variance again, and then given that noise and your starting image, you generate a noisy input sample for that step. You input this noisy input sample into a network the goal of the network is to predict the noise, not the mean, but this is one practical way of doing it. The goal of the network is to predict the noise at that stage. And then your optimization is, since you already know the noise that you put in and you know what the network estimates, you are trying to minimize the error between these two and pick network parameters that will minimize this error. So that's the training part of this. This particular approach that I'm describing here is this DDPM approach. There are a few others that I'll give quick references to. So this is what happens during training, and then during sampling, you start at the last stage. You generate again random Gaussian noise, and then you try to go step by step through your diffusion stages, if you will, and you predict noise using the network that you previously trained. And then given that noise prediction, you form a prediction for the mean for the previous stage. And then once you have that mean, now you generate another sample and then decrement your step and repeat. This is how practically this is done. I think there's a question there.
How do you decide the number of the stage, capital T?
Yeah, it's a parameter that you can select. Usually, I think that's a very critical parameter. It's usually very large. It can be as large as 1,000. So that's a parameter that you select.
I see.
Yeah, and it's again, I emphasize that usually you want to make the transitions from state to state relatively small, and so that requires very fine stepping between the stages. Okay, but this is a good point to lead to one of the other papers. So as I mentioned, this particular model, the DDPM model, requires very fine steps, and then you go one step at a time. And therefore, a disadvantage of this is that sample generation takes a long time, because you have to pass this through your network 1,000 times, essentially, to generate a sample, and that can be pretty slow. So there's a lot of interest in making this process faster. So there are papers coming up. So this is one method that allows you to skip some of the steps in your sample generation. So if people are interested in.
Can I ask one more question?
Yes, of course.
Is your method associated with diffusion tensor imaging or different diffusion?
No, it's not. Actually, I'll if I can get there, I have some connection that I'll try to form at the end. But no, it is not. It's not connected to diffusion tensor imaging. So I guess the idea is that the original method that was developed was related to thermodynamics. So that's where the diffusion idea, the name, came into this, but it is not related to diffusion MRI. I mean, not closely, let's say. Yeah.
Yeah.
Okay. So so just very quickly. So if you do this and generate some images using this method, these are some images from the DDPM paper. So they've trained their network on images of celebrities, and then they sampled images, generated images of quote celebrities from their network. You can see none of these people are real, but they are learned. They are generated from these learned distributions of how celebrity faces look. Okay, and then here's another quick example. Right. Okay, there you go. These were images of bedrooms. So these are images that were trained, there was a database of images of bedrooms, and the diffusion networks were trained using those images. And then these are samples that were generated from those afterwards. Okay. So now, all of this is good, but if you recall at the beginning, when I talked about Delhi, there's one additional step. So the way that I've described things so far is just you learn from a set of images and then you generate samples from that distribution. But there's this text prompt here, which starts guiding the process as well, right? So this is some kind of additional information, some side information that you can provide these networks. So how does that work? It's actually the basic idea is fairly simple. So if you have this Y, which contains some information about X, so you can add that as a condition in your probability, transition probabilities, and then that kind of helps you learn this extra condition about side information. In the case of text, for example, usually a method is used to condense that the natural language processing is used to condense that information into a vector that gets passed into your neural network that learns from the images. So the network can kind of try to learn the correlation or higher order dependencies between that vector and the images that it's seeing as sample images. So this is actually very, very cool. And this is what got me really interested in looking at this for my work. I do medical imaging related work. So this guidance was what I was interested in. And the references, some references for that are here at the bottom of the screen. So very, very useful stuff. So a couple of other kind of improvements over the last year or so. There's a lot of interest in looking at latent diffusion models. And so the way that I've described the diffusion process earlier is based on pixel level diffusion. So we have an input image and we try to learn the characteristics of that image. The challenges are when you have very high resolution images, the training and learning is more difficult. So people have thought about, well, why don't we compress the data before we apply this diffusion process? So instead of learning, oops, there's a typo here, instead of learning over X's, which represented our images, they learn over diffusion, they learn over latent variables. And here's an idea illustrated. So you have an image, and then you pre-train an autoencoder, and once trained, you use the autoencoder to process your sample. So you take your image, you pass it through an autoencoder. Now you have a latent variable Z. The Z goes through this diffusion process, and then once you generate a sample, you can always pass it through the decoder in your autoencoder to get back your image in pixel space. This works really well, and it has really allowed people to build much bigger models, much higher resolution images, and so on. So these latent diffusion models are a very hot topic now. You may have heard, if you've heard about stable diffusion, for example, it uses these latent models. Okay. Now, the other thing that I will mention that I think is very cool is these conditional controls in this context. So there's this recent work that came out that's called ControlNet. So this augments these latent diffusion models with, again, side information like conditional inputs such as edge maps or segmentation maps or key points and so on. And those guide the image generation. For example, here's a figure from their paper. So here's a source image. This source image is used to produce, you apply an edge detector to this, and you get the edges in this image. And now, when you want to generate your sample, you provide this edge map to your network. So it will generate images that are consistent with this edge map. And here are the samples that, four random samples that came out of such generation. You can see that it keeps the general edge information, but it's able to generate quite a variety of samples from this model. Okay.
May I ask you a quick question?
Please.
Was the edge input some of the additional variables you were conditioning on?
That's right. Yeah, exactly. Yeah, exactly.
Okay.
Yeah. So this
Thank
is passed as kind of like the side information for condition.
Great.
Exactly. Yeah. And there's so much more in this paper. I mean, I just show one example here in the interest of time, but you'll see that they've used things like segmentation maps, so you can draw ROIs and say, oh, I want a cat here, and I want grass here, and I want whatever, and it's going to generate samples that it's really super fascinating. And then now this is where I may disappoint statisticians, because it turns out that a lot of the very nice assumptions that I presented at the very beginning in terms of these Markov properties and Gaussian noise and so on are unnecessary for these to work. And so that's very nice for modeling this, and perhaps was good for motivation. But this paper, it's called cold diffusion. It's shown that you can do this by applying almost any arbitrary degradation on the images. So here's their example. So you can see that the first one is degradation through noise. Second one is degradation through a blur function. So you can blur and then deblur to generate samples, and a bunch of other things. They can do it with masks. They can like pixelate and then undo this process as well. So this is also very interesting because it suggests that you should be able to use very different degradation models excuse me, in this generative process, and it will still work. So yeah, very interesting work that came out. Okay, so let's see how much time I have. Okay, so I'll maybe talk quickly about some of the things that I've done with this. Again, the work that I've done here is really pretty trivial, but for my applications, I was just kind of interested in looking at these. I deal with a lot of inverse problems. I work not exclusively, but primarily on MRI imaging, and I deal with a lot of inverse problems. So I was playing around with these guided diffusion models to see if I can use them in my work, and I'll just show you a few examples, very illustrative. Okay, so one of the problems that we deal with is super resolution. So I wanted to see if I can formulate super resolution as a guided diffusion modeling problem. And if you remember this guided model, we have this conditioning information that we can pass along together with our kind of images that we use for training. And for super resolution, basically what I've done is I've used a set of, in this case, T2 weighted MRI images as input. This is what I want to model. And these are the high resolution samples. And as side information, I passed a low resolution version of this image. So I want to use this to guide the diffusion process. But I want to be able to generate samples from this high resolution image. Okay, so if you apply, if you use this data, so here's a low resolution image, the corresponding high resolution image. Here's a sample that's generated through this diffusion guided network prediction. Here's another slice, the low resolution image, the unknown image to the network, the high resolution counterpart, and here's one sample generated by the network, guided by this low resolution side information. Okay. Other problems that I'm personally interested in, I'm interested in contrast synthesis. So this refers to the task of predicting an MR image that's acquired by one type of contrast, for example, T1 weighted contrast, given another type of contrast of the same anatomy. So this is a T2 weighted image, and this is a T1 weighted image. And I want to be able to synthesize a T1 weighted image given a T2 weighted image. So again, using the same model, I can say that I want to model T1 weighted images, but I want to condition them using the T2 weighted image. And I learned this diffusion model using these pairs, essentially. That's what I train. And then if I do that, just a couple of samples. So this is the T2 weighted image. This is the T1 weighted image that's unknown to me. This is just the truth, if you will. And then here are some samples that are generated using diffusion guidance. All right. So I also wanted to include this just for visualization. So these are a few of the steps through the diffusion process for this particular problem. Again, if I recall correctly, I've used 1,000 steps here. So these are only 9 of them. So this is the original, the pure image that was generated at stage T, and then it was guided in this direction back to generate this image at the end. Okay? Just for visualization, that's helpful. A couple of other things. I'll maybe keep this quick. Also, I'm very interested in accelerated MRI. So that's one of my primary research areas. So I've used this for this as well. So you can here on the right-hand side see an image that is reconstructed from very few measurements. So this is using only 64 measurements in K-space, which are we make measurements in MRI. So this is about 6 times accelerated. You see a lot of artifacts that are due to that acceleration. And really, this is the fully sampled image. This is what I would like to get. So again, using the same process, if I provide this accelerated image as kind of side information and try to generate a sample from the full image, these are some of the images that I get. So this gets input into the trained network, and these are the predictions that the network generates. They are fairly decent. So it sounds like this could be used for image formation, image reconstruction guidance as well. Let me skip this. So maybe I hate to do it here, but I'm running out of time. Maybe I can. I've also used it for diffusion MRI, just because there are multiple diffusions. I thought that would be cool. So I thought, using a diffusion model for diffusion MRI would be interesting. I don't know if I write a paper how I'm going to distinguish between the two diffusions in the text, but anyway, so for those of you that are that may not be familiar with diffusion MRI, we acquire when we do imaging, we can sensitize the signal in MRI to diffusion of water along different directions. So if you do imaging with sensitivity to diffusion along different directions, you can put all of that data together and come up with something like a tensor model that represents diffusion in each voxel, and that's very much used in particularly in neuro applications, but in other applications as well. Of course, this is time consuming. If you want to acquire data along many different diffusion directions and diffusion weights, that takes a lot of time. So accelerating this is a really important research area. So what I have done in this case is the following. So I picked a particular direction, and I want to generate an image out of this direction. So I was able to generate a clean sample by using I've used Human Connectome project data for this. I'm able to come up with a clean version of diffusion MRI data for a particular direction by some prior modeling. I use very high dimensionality data. do a tensor fit, and then use that tensor to predict what the image would be along that direction. So I end up with a clean looking sample. And now what I want to be able to do is learn this image, but I want to provide as guidance some side information. And then this side information is images acquired along other diffusion directions. And you'll note that these are actual images, so they're noisy. And then a reference, no diffusion weighted image. So this also seems to work fairly well. So in this case, you see these 7 images as the guiding images. This is kind of provided as side information to this network. So if I were to acquire this image, of course, it would be noisy, and this is my target. And but if I were to use 90 of these acquisitions instead of only 6, and then fit a tensor to it, and then use the tensor to predict the image along that particular direction, I could get a clean image. This is my reference image, if you will. Now, in this process, just using these guiding images and using the guided diffusion model, I'm able to predict an image that looks fairly clean along this direction. This is another use of the diffusion model in an inverse problem.